about bonding last time there during our lecture lab. We talked about the two different types of bonding, which is ionic bonding and covalent bonding. Remember that ionic bonding is always between a metal and a non-metal, where we have a transfer of electrons from the metal to the non-metal. The result of that is we create a ionic compound. We create two ions, a positively charged ion, which is a cation, a negatively charged ion, which is an anion. And it is the attraction between the different charges that really holds that unit together. There's absolutely no sharing of electrons in an ionic bond. And that is different than a covalent compound where we actually do have sharing of electrons. That is a result of really two nonmetals or so coming together. Because of those periodic trends that we talked about, pretty much what happens when we get two nonmetals together, and because they are located pretty much in the same spot on the periodic table, they all want to basically keep their electrons and kind of take somebody else's electrons. So what ends up happening is the best they do is sharing. And as we talked about, there's sort of degrees of sharing. There's equal sharing, which is known as a non-polar covalent bond or just a non-polar bond. There's also unequal sharing of those electrons, which is referred to as a polar covalent bond, or most people just call it a polar bond. What helps us determine sort of the degree of sharing or how the electrons are sharing, as we talked about last time, is we can actually use the electronegativity values on that table that we saw, where it runs from 0 to 4. If you have that table available to you, you basically can subtract the two values in that table for the two elements within the bond. And if you get anywhere from 0 to 0.4, it's considered a nonpolar bond, which is considered equal sharing of electrons. Anything above 0.4 to below 2 is considered a polar bond, which means we have unequal sharing of electrons. And anything typically above 2, but not in all cases, but anything above 2 is typically ionic bond, which means we do not have sharing of electrons. We have that positive negative attraction that occurs. As we also talked about, if you don't have the actual values available to you, you could use in general the general trend and electronegativity to help you determine whether or not you would have a polar bond or a non-polar bond. Remember that if you're comparing two guys that are in the same period or row there, the guy further to the right will be more electronegative, and for sure it's going to be a polar bond. If you're comparing two guys that are in the same group, the guy further up will be more electronegative, and it will result in a polar bond. The only thing you really, in most cases, has to worry about is, as we talked about, there is sort of a diagonal relationship in terms of electronegativity, where you can get, for example, carbon and sulfur. They are diagonal of each other on the periodic table there, but they do share the same electronegativity, which will result in a non-polar bond. But probably 9 times out of 10, you could safely make a pretty educated guess by just using the general trend on electronegativity on the periodic table to decide is it going to be polar or non-polar. We finished up talking about how to draw Lewis structures really for covalent compounds, and there's several steps that you want to follow. The first major one is to count up the total number of valence electrons there are within the actual molecule or ion you're drawing. Remember that if it is an ion, you do need to adjust the total electron count, either up or down, depending on whether it has a positive charge. Thank you. If it has a positive charge, obviously you need to subtract from your total. If it has a negative charge, you need to add to your total. The next thing you want to do is arrange it in a logical arrangement. So the least electronegative atom should always end up in the center. You should never have fluorine, which is the most, in the center, and you should never obviously have hydrogen in the center, because as we talked about, hydrogen pretty much just needs 2 electrons only to get itself to helium to be a noble gas. So it should never be there. Everybody else pretty much needs 8. So once you get that arrangement, 1 single bond from the center atom to each of the outside atoms. Whatever electrons that you have left should go on the outside atoms in pairs of dots until each one meets the octet rule of 8. If you fill up all the outside atoms and you still have electrons, then you go to the center atom and also put it on as pairs of dots. At that point, you really should have been done with all your electrons. The last thing you want to make sure is, did everybody meet the octet rule? Obviously, except for hydrogen. And if somebody did not meet the octet rule, that's really when you should try to make a double bond, and you want to sort of exhaust all your double bond sort of options. Remember that when we make a double bond, we just don't draw the line. We're actually taking a pair of electrons, which are those dots on the outside atoms, and basically bringing them in to make the double bond. If your double bonds does not help, then you may have to move to a triple bond to get everybody to 8. Works the same way with the triple bond. We're just going to take another pair of electrons in to make that triple bond. And if you follow sort of those rules, you usually will end up with a pretty good Lewis structure. And, any questions on any of that there? I think we did a couple there towards the end. So why don't we do a few more here just to make sure. So I think maybe let's do CO3 2-, which I think was on your chart there. Let's also do SH2. Let's do NH4 plus. Let's draw N2. And let's see. Let's do CO2. And I think that's good. Well, I'm going to stick with those for now. All right, draw the correct Lewis structures for each of these. Obviously, the other important thing, as we talked about, right, number of valence electrons equals the group number, right? It's a very quick way that you kind of get those guys. Take a few moments and draw these guys up. See what you come up with. Oh, by the way, let's do one more. We'll have to fill it out here. SO2. Let's do that guy. That we're doing. So we will start with CO3 2-, which is carbonate. So remember, the first thing we want to do really is calculate the total number of valence electrons, as that is the number that we need to end up with. So carbon here is 4, I believe, and we have 3 oxygens at 6 each. Here we do have a -2, which means it did gain 2 electrons. So we do need to add that to our total. Otherwise, we're going to be a little bit short there. So that's going to give us 24 valence electrons. Here, carbon, again, and oxygen are in the same row on the periodic table. So if you weren't sure, oxygen is further to the right, which means it's more electronegative. The carbon is less electronegative. Plus, there's only 1 carbon and 3 oxygens. So carbon should go in the middle. We should do an oxygen on each side. Again, you could do the oxygen up on top or on the bottom. It really doesn't matter. We're going to make 1 covalent bond from the center to each of the outside atoms. That's going to be 2, 4, 6 electrons. That is going to leave us 18 more to go, which are going to go here on the outside in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have basically put on all my electrons, and kind of like the one we did previous, we do see here that the carbon is actually short. It only has 6 electrons. All the other ones do have 8. So this again is the place where we want to kind of fix that by making a double bond. In this case, every single oxygen is identical to each other, so you can really make the double bond at any place you want. I'm going to go with the top guy here, and I'm going to bring those electrons in to make the double bond. And when I do so, I will end up with a double bond up on top, and we will still have our single bonded guys over here on the sides. As we also talked about, since it does have a charge, we typically want to put brackets around it and the charge on the outside there. Was there a question? Yeah. Yeah. Which side the dots are. Truthfully, again, it really doesn't matter. Or if you're asking like on the double bonded oxygens that we're asking, kind of, yeah, it really doesn't matter as long as you have the correct number of dots, unless you find somebody that's like super picky. Traditionally, on like a double bonded oxygen, people will usually put it on the left and right hand side of it. But really, if you put 2 on top and 1 on the left, it's not really wrong or anything like that, unless you find somebody that's like really, I don't know, super picky. But as long as you have the correct number of dots, it should be okay. Yeah. Again, really the main rule is, as we talked about, is really no more than 2 per side. So you never want to go more than 2 per side, but as long as you got 2 on the sides, okay. Other questions? We could also, as we talked about as well, draw the 2 other structures which are related to each other. They are what are referred to as resonance structures. And basically what we're doing is, because we do have the option of making perhaps a double bond over here, we could draw another equivalent structure that is referred to as a resonance structure. Usually has like this arrow between them. And we could also draw a third one in this case, which would be the double bond on the left-hand side, which again would look very similar, except that we double bonded obviously on the left-hand side here. And all three of these would be proper. That's a mistake there, so ignore that. These are all, you could draw either one of these guys. Any one of these guys is sufficient. And as we might have talked about, really because those electrons are needed to come in to make the double bond, they are what are referred to as being delocalized, which means at any given point in time along carbonate, you know, those double bonded electrons are kind of moving around. So they may be at the oxygen on top, they may be the guy to the left, they may be the guy to the right. The real structure is somewhere in between all three of those. So we could draw, if you just need to draw one, you could draw any one of those. If you're asked to draw all the resin structures, you would draw all of them. And it's really just as simple as really moving the double bond to wherever possible you could have made it a double bond. Any questions on that particular one there? All right, then let's take a look at, we'll do SH2 down here. So SH2, we got 6 for the sulfur plus 2 times 1 for the oxygen or hydrogen, which is 8. In this case, since hydrogen obviously cannot be in the center, that leaves us our sulfur in the center with hydrogen on each side. At this point, we're going to just make a single bond. That is 4 electrons. We have 4 more to go. We cannot put any more on hydrogen because it is full at this point. So we do need to go to the center. And just like before, we would do our dots there on the center. That will now give us 8 total electrons. And everybody has 8, including sulfur there. Hydrogen has what it should have, which is just 2. Remember, no dots on hydrogen or anything like that. Any questions on that particular one there? Okay, rolling into the next one, which is NH4 plus. So we got NH4 plus. So nitrogen is group 5. There are 4 hydrogens each at 1. In this case, though, we do have a positive charge, which means it lost electrons. So we do need to subtract because of that positive charge. That's going to actually give us 8 valence electrons here as well. Nitrogen, for the same reasons as previous, will go into the middle. Hydrogen will go on the outside again because it cannot go to the middle. At this point, we're going to make 1, 2, 3, and 4 bonds there to the center guy. That actually is going to take up all 8 electrons to do so. That means nitrogen does have 8. All our hydrogens have 2. And that is all they wrote on that one there. Yeah. Any questions on that? Yeah. Yeah, so you don't want to think about it like that because you will end up with the wrong picture. So you don't want to think about sort of piecework, if you will, like, okay, this guy started with 5, I got to get him to 3 more and stuff like that, because you will end up with the wrong picture. What you want to think about is like when you count up the total number of valence electrons, that is like the total amount of electrons you need to distribute to everybody to make everybody sort of happy. And that's the best way to think about it, because sometimes people will do what I think your question is what I sometimes call piecework, when they'll go, well, nitrogen's got 5, he needs 3, this guy's got, this, and I need to figure out where all the, dots should go to fix it. And you really will usually end up with the wrong picture and not the right amount of electrons. So the best way to think about it is when you sort of add up this number here, that's like, okay, I need to distribute those electrons properly to everybody. It's really nobody's electrons per se, we're just going to try to get everybody to that octet role. And it's a better way of sort of thinking about it. The maximum amount of bonds a single atom can make, usually they will max out at like a triple bond, usually as far as you go. Yeah. And that's also why you should sort of reserve double bonds and triple bonds to fix the octet rule, because the idea here is we're really trying to distribute all those electrons to get everybody to meet the octet rule. And sometimes, again, the other mistake that people make is they just want to like double bond, triple bond, like right out of the box. And it's usually the wrong sort of structure that you end up with. So best way to think about it is this is how many electrons I need to distribute them to get everybody to 8. After I distributed them all, if I didn't get everybody to 8, then I should think about double bonds and triple bonds to get everybody to 8. And that's the best way to do it. At that point, you really won't go over a triple bond pretty much. Yeah. Other questions? Okay. So that was NH4 plus. So I think the next one was a CO2, right? Yeah. So CO2 will do. So same thing here. We're going to look at the carbon, which is 4. We got 2 oxygens, which is 6. That's a lot of math, but that's like 12 and 4 is 16, I hope. Yeah. All right. So in this case, again, carbon, oxygen, same row. Carbon, the least electronegative, should go in the middle. We're going to put our oxygens on the outside here. We're going to make 1 bond, 2 bonds. That is 4 electrons, which means we got 12 more to go to distribute. So that is 2, 4, 6, 8, 10, and 12. At this point, we have now distributed all 16 of our electrons. Is everybody good? The carbon is not good. It is short there at 4. So we're going to make our double bond to try to fix it. We could go either side. We're going to take one and drop it in there. And when we do so, we will end up with a double bond to the left, a single bond over here to the right. And at this point, did we fix it? We did not. And carbon has got better, but it's still short. It's at this point, you may be tempted to like, I want to lay up a triple bond, but I would not do that because we still have an option to make a double bond on the other side. So again, you kind of want to exhaust all your double bond options before you go to a triple bond. That's sort of the best sort of way of doing it. So we can make a double bond on the other side here by also bringing in a pair of electrons. And when we do so, we will end up with a double bond over there. We'll end up with a double bond over here. Now, when we look at the carbon, it's got 2, 4, 6, 8. Each of the oxygens still have 8, and we still only have 16 electrons in our picture. So in this case, by actually double bonding on both sides, sort of again exhausting the double bond, it makes a pretty good picture. For reference point, could you have triple bonded? You could have laid up like a triple bond over here if you wanted to, I suppose. And for reasons that we really don't get into in this class, this is actually a worse picture than this one. This is a much better structure. So usually, again, if you follow the sort of rule of fixing it with the double bonds and exhaust double bonds before you go triple bond, that usually leads you to a better structure. There's something known as formal charge, which we don't really get into in this class. When you take 1A, you do, and you can use something like formal charge to determine which one is a better structure. And if you did that, the guy on the left there that we originally drew is actually a better structure than the guy with the triple bond. So there are some other reasons as to why you kind of want to exhaust your double bond before you go into a triple bond. Question on that? Yeah. There is not at this point. We pretty much, because we needed to make both sides double bonded, at that point, there's no other options to make another double bond, right? So if we happen to have fixed it, let's just say, for example, we fixed it by just making like the double bond on the left, that was the only thing we did. Then we could have, made a resin structure. But in this case, there's no other place after we finished drawing the structure. Other questions? Yeah. Yeah, so pretty much there's 2 simple rules, and the first rule is pretty much every single element in a Lewis structure needs to get to 8 electrons. That's the octet rule. So that's a really important rule for bonding. So everybody's got to get to 8, except for hydrogen, just should only have 2. So that's the only guy that should have 2. Everybody else should get to 8. Are there exceptions? There are, and we'll talk about a couple of exceptions in a bit, but for the most part, the goal is to get everybody to 8. The reason for that all comes back to what we talked about with electron configuration, right? When we get everybody to 8 electrons, that moves everybody basically to the noble gas configuration, right? Or a noble gas electron configuration, and that's a really stable thing. So that's why everybody shoots for 8 electrons, except for obviously hydrogen, which obviously just needs to get to helium, which is 2 electrons. So the carbon, so by sharing these electrons here, so when we look at this oxygen and we look at this oxygen, these guys all have 8, 2, 4, 6, 8. Now the carbon's actually sharing all those electrons with both oxygens, which means the 2 double bonds, or the 2 lines on the left represent 4 electrons. The 2 double bonds, or lines on the right, represent 4 electrons. So that gives it 8 electrons by sharing electrons. So if we did it with like the dots, which I think we might have looked at earlier, you know, this carbon in the middle by sharing those electrons on both sides gets itself to 8. Basically, yeah. Other questions? Okay, let's see. We did that one, that one. The what we got going there? We got nitrogen. So we did that N2 next. All right, let's take a look at N2. N2 is just nitrogen, so that is pretty simple here. That's going to be 2 times 5. That is 10 valence electrons. In this case, there's only 2 atoms, so there's no center atom. So you're just going to go side by side, basically, on this deal. And you may think, do I need to do kind of the same thing? And you can do the exact same thing. We're just going to connect them with a single bond. That gives us 2 electrons. We got 8 to go. We could do the same things we did, just kind of put it on one side here. So 2, 4, 6, and then 8. At this point, the nitrogen on the right's all good. The nitrogen on the left, not so good, right? It's only got 4. We'll do our normal thing here. We're going to take 2 electrons in and make a double bond. At this point, we will end up with a double bond in the middle. Guy on the right is still good. Guy on the left got better, but he's still short. He only has 6 electrons, 2 on top and 2, 4 for the double bond. So at this point, we have no place to make another double bond. Now we would go to a triple bond here, and it works the same way. We're going to take those pair of electrons and bring them in to make that triple bond. When we do so, we will end up with the triple bond in the middle. We also end up with our dots up on top. And at this point, we still have 10 total electrons. Each of the nitrogen have 8, 2 on top and 6 in the triple bond on each side. And that is the correct structure and how something like N2 gets to a triple bond. So kind of keep sharing those electrons to give each of them basically 8. Any questions on that one there? All right, lastly, I think we had on the list there was SO2. SO2 is 6 for the sulfur, 2 times 6 for the oxygen. That is 12, 18 valence electrons. Here, the sulfur should go in the center. The oxygen should go on the outside here. And we're going to do our same thing. We're going to make a single bond. That is 2 and 4 electrons. At this point, we're going to fill up our outside. So that is 2, 4, 6, 8, 10, and 12. At this point, we have now placed 16 electrons. We actually still have 2 more to go, and they should go into the center atom as dots. And by the way, that is how you get those guys on the center atom with dots, which should be there. At this point, we look at everybody, and oxygen is good. The sulfur is not good. It's got only 2, 4, and 6 electrons. So here we're going to make a double bond. You could choose either oxygen to do so. I will take these guys here and bring them in to do so. When I do, I end up with a double bond on the left. And we could also draw a resonance structure for this one because we could have double bonded on the right. And if we did, it would look pretty much the same, except the single bond obviously is over here on the left. And that is the proper structure for SO2. If you follow the way we just talked about and just did it, you will get the right structure. If you do not, you will probably end up with double bonds on both sides and no dots on the center atom, which is wrong, by the way. So you want to make sure that you distribute those electrons sort of properly. Any questions on how to draw Lewis structure? Yeah. They are, yes. So again, because they're the same group, electronegativity increases as you go up and to the right, which we know by just looking at them. Oxygen is more electronegative than sulfur, which is why sulfur is in the middle. Yep. Yep. And if we also had to make a guess here between the bonds, between the sulfur and the oxygen, we can make a pretty safe guess that these guys are polar bonds, with the more electronegative heading towards the oxygen. If we draw those kind of bond dipole arrows we talked about, you can have them actually go that way, right? We have those 2 polar bonds heading towards the oxygen be more electronegative, which means the oxygen in this case would be more partially negative. The sulfur would be more partially positive because the electrons are being shared unequally towards the oxygen side. Question on how to draw Lewis structures. Clearly, you need to know how to draw Lewis structures correctly. Yes. Okay. All right, so we did that guy here. All right. All right, so we sort of talked about resonance structures, but let's also talk a little bit about bond length. Bond length is the distance between obviously two atoms within a bond. And you don't have to obviously memorize this chart or anything like that. But if we look at this chart, these are the lengths for different types of bond. If we compare bonds for carbon and carbon, that's the carbon-carbon single bond, which is 154, double bond 133, and triple bond 120. What we typically see is a single bond is longer than a double bond. When you make that double bond, bring those electrons in, everything gets smaller. Everybody gets kind of closer to each other. When you take another set of electrons and bring them in to make that triple bond, it's going to pull everybody even more closer to each other. And what we typically see is when we look at a double bond to a triple bond, double bond to a triple bond, and a single bond to a double bond, we do see that the single bond is larger, as we can see here with nitrogen and carbon. Nitrogen is 143 for a single bond, gets smaller, 138, and even smaller in terms of a triple bond. And that does have an effect on bond strength. So in terms of bond strength, a double bond is stronger than a single bond, and a triple bond is stronger than a double bond. They're not like 3 times as strong or anything like that, but is in relationship to it. I usually think about it like a pencil. If you grab a brand new pencil out of the box, it's nice and long, you could take it and snap it, no problem. You take that same pencil after you've taken a couple of chemistry exams, you got like a nubbin and an eraser, right? It's super hard to try to break it, right? It's very hard because everything is close to each other. It's held really tightly. So it kind of works the same way with bonds as well. Triple bond, much stronger than a single bond. Now, we talked about resonance structures as we were drawing our pictures, but resonance structures really do arise from situations where you do have to sort of make a double bond, and situations really where there are multiple options of where you could make that double bond. As we talked about with CO2 or CO3 2 minus, those double bond electrons really are delocalized, which means they're really just traveling around from kind of outside atom to outside atom. So again, at any given point in time, you really could kind of up on top, for example, in this one, to the left or to the right. So we could draw really equivalent type structures for a molecule like CO3 2 minus to illustrate that. As I mentioned before, usually in between those structures, you'll see this kind of 2-headed arrow heading in both directions to indicate that they are resonance structures. As I mentioned before, you do not have to draw all the resonance structures unless you're obviously instructed to do so in a problem. If you're not asked to draw resonance structures like we did here with CO3 2 minus, you could draw any one of the 3. If you are asked to draw a resonance structure, you should draw all the possibilities that you can. And again, it's just wherever you could possibly move that double bond is what you would draw. And here's a few examples. That's ozone, by the way, and don't worry about the charges. But again, basically, we could double bond on the left here. We could also double bond on the right. And we get this sort of 2 equivalent sort of structures to each other. Again, because those double bond electrons are moving around. And then obviously we did carbonate earlier. The charges, by the way, is where the -2 comes from. That's actually the charge where those come from. It's actually on those oxygen atoms in carbonate. But again, we can move it around from one place next. Benzene, if you ever take organic chemistry, benzene ring looks something like this. It's a 6-carbon ring. Each of these little points are carbons. And it has some double bonds that are in there. And just like anything else, you can actually move the double bonds around to different locations. And you'll sometimes you ever see benzene, and maybe you have and didn't know what it was, but sometimes also draw just like a circle in the middle to indicate that those double bond electrons are kind of constantly moving around and delocalize over the entire thing. Good news is you don't really see too much of that until you take organic. And if you do, good luck with organic now. It wasn't my favorite, all right? You know, it's all right. It happens. Here's just another example. Let's get through that one. Now, there was an earlier question about, you know, should everybody kind of get to 8, and does everybody want to get to 8? And the answer is yes and no. And there are several exceptions to the octet rule. And as we're going to talk about these, for our purpose in this class, you just need to be aware of that there are exceptions and what those exceptions are. You will never be asked to draw an exception to the octet rule. Everything that we draw in here should obey the octet rule until you get to like 1A, and then you can forget about the octet rule and all that good stuff. But for here, we basically will obey the octet rule, but there definitely are stuff that does not obey the octet rule. The first sort of exception to the octet rule is what's referred to as an incomplete octet. And much like the name implies, there are actually some elements that are perfectly fine with less than 8. And the main one that we usually come across, even though really that may not exist, is actually boron. Boron is what is known as being electron deficient. And it actually is really just perfectly fine with less than 8. It actually just wants to get to 6. Aluminum is another one. And again, we don't really come across too much of aluminum or beryllium in sort of covalent bonding, but those kind of 3 guys are ones that are sort of electron deficient and okay. But boron really is. So here, if we drew this for boron, we wouldn't need to make a double bond or anything. Actually, boron's all good just like that, with just 6 valence electrons around it. So an incomplete octet is one exception that you sometimes will see. An odd number of electrons is another exception that you do commonly see, or not commonly see, but do come across. Odd electron molecules means that you basically have an odd number of valence electrons. And what that means is at some point, you will end up with a single electron by itself. They are sometimes referred to as like free radicals. They have a single electron, makes them super reactive because they really don't want to have a single electron. So they're very, very reactive. So a lot of like molecules in atmospheric chemistry, like chlorines and stuff like that, will end up with like an unpaired electron, makes it really, really reactive. Now, the one exception to the octet rule that when you do get to 1A that you will see nonstop is this one. And that is the expanded octet. The expanded octet means that there are certain elements that actually can go above 8. So they could go above 8. They could go all the way up to like 12 electrons around them. And if you look at the periodic table and you find our good friend sulfur, and you go to the right and you go to the left and you go down, those are pretty much everybody that will kind of go into the expanded octet or have the ability to do so. I won't say they always will, but they have the ability to do so. And that is because, and really what we're talking about there is kind of nonmetals, kind of just where sulfur is at and down. When we look at sulfur, it is on period number 3 of the periodic table. Period number 3 of the periodic table refers to what energy level when we talk about electron configuration? He is on N equals 3, yes. On the 3rd energy level, what orbitals are available? S's, P's, and that is the 1st energy level where we start to see d orbitals available. And because they have actually d orbitals available to them, even though they may not be using them themselves, they have a place to stash the extra electrons. So they're able to kind of use those d orbitals to add more electrons and go over 8. That means, though, if we look at something like nitrogen or oxygen, which is period number 2 on the periodic table, like nitrogen, oxygen, that is N is equal to 2. On N equals 2, there's only S and P, no D, which means those guys can never, ever, ever, one more time, ever go over 8. They got to stick to the octet rule for sure. So that is a very common exception that you do come across in 1A. Again, here, everything will obey the octet rule in our class, but you know, you can't go over 8. And that's why sometimes, for example, obviously SF6 is an example that if we just connected up the fluorines here it would look something like this without all the other dots. And when we look at sulfur, 2, 4, 6, 8, 10, and 12 electrons around it. So that's a very common sort of exception to the octet rule. Also, why if you Google things and you draw things just based off of Google, you may not know what you're drawing. But you know, if you drew something like sulfate, which looks like this with single bonds, everybody obeying the octet rule. If you Google it, you will sometimes see sulfate drawn like this with some double bonds to sulfur. And in this particular case, the sulfur obviously went over 8. And, you know, if you're told not to go over 8 and you draw that, that's bad. Yes, that just makes me think like, you know, you looked it up on the online. This is not always good. This is really what you should end up with based on our rules and following the octet rule. I know people look up answers and just go Google it. You know, following our rule here where everybody obeys octet rule. I will say, oddly, as we talked about with the triple bond on CO2, based on formal charts, this is actually the much better structure, which is why you oftentimes will see it online and drawn that way, because this is actually a much better structure on the right. But for our purposes, you will obey the octet rule and draw it like this, not like the guy on the right, even though technically speaking, it is the better structure. When you get to 1A, you'll draw it like the guy on the right, and that will be the correct structure. Any questions on exceptions to octet rule? Again, everything will follow the octet rule here in this class. You should be aware of the exceptions. But you won't have to draw any of those again until you get to 1A. The 3 exceptions? So incomplete octet, odd number of electrons, and expanded octet. No, that'll be sufficient for us. Again, we don't delve too much into it, and you'll be very happy that we don't do that, because that cuts down on the geometry that we need to talk about now. When you get to 1A, there's a ton of geometries that go with expanded octets and stuff like that. So they save that torture for 1A when you get, I don't know. So let's talk about molecular geometry. The good news here about geometry is not angles and stuff. Oh, I guess it is sort of. So molecular geometry refers to sort of the 3-dimensional arrangement of all of our atoms in space. We really can sort of predict the molecular geometry based on the central atom and how many electron pairs there are around the central atom, and really how many bonds there are around the central atom. So if we draw a correct Lewis structure, you could do molecular geometry and determine that. When we do molecular geometry, it's always about the center atom. So when you got somebody in the center, that is really the most important one to determine sort of what the overall shape of the molecule is going to be. Now, when we talk about this, this is based on electrons. There's this idea, obviously, that electrons obviously are negatively charged, which means they really don't want to be near each other. And what happens is, depending on the type of electrons that are there, be it the non-bonding electrons, be it the bonding electrons, when they get near each other, there's degrees of I want to escape. And what happens is the electrons try to move away from each other. They clearly can't completely escape, right? Because we're not having transfer of electrons. But as they move around to sort of find a happy medium and a place where they can be happy to stay, that is changing the overall shape of the molecule. So as those electrons and those bonds sort of move, the overall shape of the molecule starts to really change. And we do get some different geometries that occur. Now, the idea of this is what is referred to as Vesper, which stands for valence shell electron pair repulsion model, which is, I imagine, why they abbreviated it. That's a mouthful. And basically, we divide everybody up into 2 categories. One category is when the Lewis structure, you have no lone pairs on the central atom. One is when you actually draw the Lewis structure, you end up with dots on the central atom or not. Now, important thing to consider when we is if you have a double bond or a triple bond in your picture, it counts as 1 electron pair and 1 bond. So when you have a double bond or a triple bond, it counts as 1 electron pair and one bond. And that's really important. We think of double bonds and triple bonds because they're really sharing electrons. They're moving around really as one unit, and they will share those electrons and are counted as one electron pair, one bond. Also, if you draw a resonance structure and you do it correctly, you'll end up with the same geometry, regardless of which one you sort of drew. It all should end up the same. So at this point, a couple of things are important. First off, we are going to be talking about two types of geometry. One is the electron pair geometry, sometimes called electron pair arrangement geometry. The other one is the molecular geometry, and one that is sometimes also referred to as like the shape of the molecule. The electron pair geometry talks about how the electron pairs are arranged around the central atom in three-dimensional space. The molecular geometry takes into account all the electron pairs, the bonds, and everything that's there, and what the overall structure kind of looks like of the molecule as everybody sort of adjusts. So we will be talking about two different types of names. So let's get into it here. First off, the most simplest one you could talk about is a diatomic molecule. So when we have a diatomic molecule, you pretty much only have two things like H2, F2, O2, HF, N2. Doesn't matter if it's two of the same element, doesn't matter if it's two different elements, doesn't matter if it's got a single bond, double bond, triple bond, quadruple bond, no quadruple bond. But if it's only two atoms that are there, the only way you can really arrange two things in space is between a straight line, right? So the geometry is always linear. It's a no-brainer. You should just put linear and move on with your life. Yes. They are basically arranged at the end of a straight line. Is basically how you will always arrange basically two things. Now, if everything was that simple, that would be wonderful, but it is not. So when we do get to guys that have three or more atoms involved, you do have to look at a couple of different things to sort of help you decide what's going to happen. So let's talk about our first sort of example of that. If we have something like, say, beryllium chloride here, we want to look at the center atom, and it's always the center atom when you're doing geometry. When we look at the center atom, it has, if we count, 2 electron pairs, and it also has 2 bonds. So first off, something with 2 electron pairs, when you have 3 or more atoms, the electron pair geometry is linear. The overall molecular geometry is also linear. It's also based on a straight line. In this situation, the only type of electrons we have around the central atom are bonding electrons. Yeah, they're within a bond. So what ends up happening is, because there's only 2 of them, this guy goes, I'm just going to go as far away from the other side as possible. They spread out based on opposite ends of a straight line, and we end up with this linear geometry, which accounts for both electron pair geometry and also the molecular geometry, because we're talking about the same type of electrons. They're both bonding electrons within a bond, and we end up with the same geometry. The bond angle is 180 degrees as you go across. So 2 electron pairs, 2 bonds, linear for electron pair geometry and linear for the molecular geometry. That obviously is an exception to the octet rule. That's an incomplete octet there. If we look at something like BF3, which is also an incomplete octet, if we look at our boron, again, the guy in the center, it has 3 electron pairs, also has 3 bonds in this case. Something with 3 electron pairs, and when we talk about electron pair geometry, is going to be what is referred to as trigonal planar. Some people will call it triangular. And basically, the molecular geometry here will also be trigonal planar. It is trigonal planar because essentially now we have an extra bond in the way. So the best that they can do because of the extra bond is they no longer get opposites of each other because there's the third guy. So what they end up doing is basically making an equilateral triangle, hence why it's sometimes referred to as being triangular. It makes basically a triangle that allows each of these fluorines basically and those electrons that are holding them to get away as far as possible from each other. Again, as the two move, the third guy is going to move up, and as they come down, he comes up, and that gives them the distance that's between them. We end up with a bond angle of 120 degrees for trigonal planar. Any questions on that there? The next one that will come across is methane. If you draw methane, it will look something like this. Again, looking at the center atom, which is always the important, it has 4 electron pairs. It also has 4 bonds in this case. Something with 4 electron pairs in terms of the electron pair geometry, which is how the electrons in 3-dimensional space are spread out. It is what is known as tetrahedral. It also has 4 bonds, which means the molecular geometry here will also be tetrahedral. And basically what happens is it makes kind of like a triangle on the outside and more of a pyramid shape coming kind of down on the bottom there. Again, here by adding 1 more bond in there and 1 more atom, we now have 4 bonds. So as they start to move, you now have 2 other things that are moving as well. So the best that they could do is get about 109.5 degrees away from each other, which is the bond angle for tetrahedral. Up to this point, when we look at the Lewis structures, there are no non-bonding electrons. And that name are the same. And that's what we saw previously as well. No non-bonding electrons here. We end up with the same name. And also on the previous one as well. No non-bonding electrons here. We end up with the same name. So when you draw a Lewis structure and you have none of those non-bonding electrons around the central atom, or no dots around the central atom, what you end up having is only bonding electrons. And bonding electrons near bonding electrons are the most like agreeable with each other. They're like, all right, I don't really want to be around you, but you know, I could handle being somewhere near you. And that's the less repulsion that occurs when you put electrons near each other. So when you do draw Lewis structures and you got no dots on the central atom, the electron pair geometry and the molecular geometry should always be the same name. It's only when we start to introduce non-bonding electrons into the mix, those dots around the central atom, that we get a lot of different electron and electron interactions that basically occur. And those interactions result in really 3 types of interactions that could occur. When we start around the central atom having these dots and bonding electrons, we can get a couple different arrangements. What we've been talking about is bonding electrons near bonding electrons, which again, like I just said, is like the most, all right, it's not too bad. The next worst situation is when you start to get non-bonding electrons near bonding electrons. That's on your Lewis structure when you draw dots and lines near each other like this. This is like a bad situation. They don't really want to be near each other, those non-bonding electrons near the bonding electrons. And what ends up happening is they try to get away a little bit further. They're able to get away a little further because when you have non-bonding electrons, you no longer have an actual atom attached to the other end, right? So it gives them a little bit more room to kind of move around and spread out. The worst situation you could have is when you get like non-bonding electrons near non-bonding electrons. That's like the worst situation. They do not want to be near each other. They both do not have atoms bonded to them, which means, again, they have even more room to spread out. So what ends up happening when we start to introduce these non-bonding electrons are, because we're lacking those bonds, those electrons are able to get further away from each other as possible. The result of that is the remaining bonds and stuff in the structure will start to move as those electrons move. And what it ends up affecting is only one name it ends up affecting. It actually ends up affecting the molecular geometry name. So the electron pair geometry will still be the same because there's still the same number of electron pairs around each other. But what ends up happening is the overall shape of the molecule will actually start to change because of those non-bonding electrons moving even further, causing the overall shape of it, basically, of the molecule to change. So let's take a look at that. First example here would be SO2. If we draw SO2 like we did earlier, we will end up with a structure that looks like this. When we look at the sulfur, which again is the important guy here, how many electron pairs does this sulfur have? It has 1, 2, double bond counts as just 1. So this actually has 1, 2, 3 electron pairs. Something with 3 electron pairs, as we talked about earlier, has an electron pair geometry of trigonal planar. So it has 3 electron pairs. How many bonds does this one have? It has 1 bond, and double bond only counts as 1. So that's a grand total of 2 bonds in this case. So something with 3 electron pairs and 2 bonds, because of those non-bonding electrons up on top, there's nothing bonded there. It wants to go like way away. And the result of that is these guys will come down as the electron pair kind of moves away. As angular. Some people will call it bent angular or bent even, but it is actually more angular is sort of the right terminology there. It has a bond angle of less than 120 degrees. So just a little bit less than what we see in a normal trigonal planar because of those non-bonding electrons being able to go up. The oxygens on the side kind of come down and creates this angled type of geometry. Any question on that? Here we see dots on the center atom, and we get different names here between the electron pair geometry and the molecular geometry when we start to get those non-bonding electrons. Any questions on that there? Yeah. So the easiest way to do this is most people cannot, in their head, myself included, sort of visualize all this thing. So the best thing to look at is you want to look at always the central atom. You want to count up how many electron pairs and how many bonds, and kind of memorize that 3 electron pairs and 2 bonds gives you an angular geometry. Yeah, that is these things that I've been writing here, electron pairs and bonds, is really the best way to think about it and know the geometries that go with it, unless you can visualize what's happening. But again, what's essentially happening is because of these non-bonding electrons, they want to get away from these bonds. So as they sort of move up and away, the result is, because everybody's connected, is these guys start to sort of come down, and we end up with this sort of overall geometry that sort of looks like this, which is sort of that angled type of geometry. Electrons move away and the other ones kind of adjust as they're moving. Other questions? It doesn't necessarily. It does cause, as we'll talk about a little bit later, is it does cause differences in terms of how the overall electrons are shared in the entire molecule, and creating like a polar molecule versus a non-polar molecule. Yeah. Other questions? Yeah. Yeah, you could have, like we talked about, you could have different, you could make it something with an isotope of an atom, because the same element, it will work the same way. Yeah. It doesn't, because it basically, because remember, this is all about electrons. So if it has the same number of electrons, it would work the same way. It would just have different neutrons if it was an isotope. Yeah. Another example, NH3. If we drew the Lewis structure here for NH3, again, looking at the center atom, which is the important, total electron pairs, doesn't matter if they're dots or lines, is 4 electron pairs. Again, dots and 3 lines. In terms of bonds, it has 3 bonds. So again, the electron pair geometry doesn't change. So it still has 4 electron pairs, which means the electron pair geometry will still be tetrahedral here. Here we get sort of a worse situation happening. We have non-bonding electrons near bonding electrons. So much like in SO2, these non-bonding electrons are going to try to escape. The problem here is there's an extra atom bonded here. So the other guys can't come all. The best they could do is kind of come down, but try to keep their distance from this guy and keep as far away from that guy as possible. And what ends up happening is we get a molecular geometry known as trigonal pyramid, because it kind of makes a triangle with a pyramid shape at the bottom here. So trigonal pyramid is what we get when we have bonds. We'll take a moment to talk about trigonal pyramid and trigonal planar. They are different. This bond angle, by the way, is less than 109.5. It's about 104 degrees. Actually, is about where it's at, 104.3. This difference in the names is trigonal planar is 3 electron pairs and 3 bonds. Trigonal pyramid is 4 electron pairs and 3 bonds. On a test, you should not just write trigonal and let me choose. I will choose like this with an X. Yes. So choose correctly. Don't do my other favorite. I think is trigonal. It was a pyramid. That clearly says pyramid on there, right? Or maybe that says planar. I'm not really sure. So make sure you do choose. Don't just lay up trigonal, because there are 2 different choices. Make sure that you pick the correct one. The last geometry, thank goodness, that you need to know is like here. Again, as I talked about, when you get to 1A, there will be a lot more. But if we look at water, 4 electron, 2 dots, which is 4, 2, and 2 lines, which is 2 more, gives you 4. In terms of bonds, it only has 2 bonds in this case. And based on how many electron pairs there are, so there's still 4. So the electron pair geometry is still tetrahedral. Now, in this particular case of water, we have all the worst things happening here. We have bonding electrons near bonding electrons. We have non-bonding electrons near bonding, dots near lines. And we have the worst case scenario, which is non-bonding near non-bonding, dots near dots. What happens is when those non-bonding electrons get near each other, they are both going to try to run for the hills and go this way. The result of that is the hydrogens also want to keep some distance, so they're going to kind of curve down. Then is we end up V-shaped. Questions on that? So what we see here is when we start to introduce these non-bonding electrons, we actually start to get differences in terms of the names of the molecular geometry. The overall shape of the molecule changes because of the non-bonding electrons. Really want to get away from everybody. And because we're lacking all the extra bonds that were there originally, allows them to move away a little bit more, resulting in the overall shape of the molecule changing. Best way to do this is, unfortunately, memorization. So what you want to memorize is how many electron pairs and how many bonds and the corresponding names is really the best way to do it. And obviously drawing a correct Lewis structure is a pretty good way to do it as well. Any questions on geometry here? Yeah. No, there's other ones that will do bent or V-shaped. You know, so for example, I think we drew this guy earlier, right? This guy right here, right, has, if we look at the central atom, 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, has 1 bond, 2 bonds. This guy as well would be bent or V-shaped, yeah. So we also drew CO2 earlier, right? What would be the geometry of CO2? How many electron pairs around the carbon? It has 2 electron pairs. Again, each double bond counts as only one, right? So one on the left, one on the right. Bonds it has 2 bonds as well. Again, double bond counts as 1 bond on the left and 1 bond on the right. Something with 2 electron pairs is what type of geometry? Geometry would be linear as well. Yeah, so that's what we saw earlier. We also did, we'll come here. We did, which one did we do there? We did this guy, right? It has how many electron pairs around central atom? It has 4 electron pairs, and bonds it has 4. Something with 4 electron pairs in terms of electron pair geometry would be tetrahedral, right? And a molecular geometry would be the same. Again, here, no dots on that central atom, so both of those names should be the same in that case, just since we're going backwards to what we did earlier. We also drew, I think we started with this guy, I think, right? Carbonate. So this here has how many electron pairs? It does have 3. Again, double bond only counts as 1, so that's 3 electron pairs. Bonds, 3 bonds. So geometry would be also the same again, right? No dots. Question on how to do geometry there? That's really the best way. Just memorize it, count the electron pairs correctly, and do it. B. It's just linear. There's really no central atoms. So there's no kind of like bond angles or anything like that. You know, so just linear is sufficient for that one, for both geometries. Any questions on that? All right. Yeah. Say it again. Here, because there's only 2 atoms involved. So anytime you have any, it's one of those diatomic ones we talked about the very range 2 atoms, a straight line, which would be